Section 1.2, we're going to be finding limits. This is our first true calculus section because limits are a calculus topic. You may have seen the limits in a pre-calculus class. Sometimes they are taught at the end of a pre-calculus class. Specifically in this section, we're going to look at two methods for finding limits. Graphically, so clearly that means we either have a graph or we get our calculator to give us back a graph and go from there. And numerically. Numerically means tables. Okay, so when you see the word numerically, it's talking about doing something with a table. Now, we just did something with a table in section 1.1, right? It was kind of tedious, yeah? But what we found is we found a slope in 1.1. We're not finding slopes in 1.2. So the tables in 1.2 are not as bad as the tables in 1.1. That's good news because we're going to do more of them, okay? We're going to start with the graphical one for today, though. But before we get to actually looking at them, we're going to talk about what we mean by them. So this is sort of an intuitive description of what a limit is. A limit is a y value you approach, but may or may not touch. Okay, so does anybody have something in your phone that like checks you into certain locations when you show up automatically? Do you guys know what I'm talking about? Like, for example, my husband and I have a Life 360 account. When I get close enough to my house, it tells my husband, Krista has arrived at home. Do you guys know what I'm talking about? Mm-hmm. Your phone is doing a limit. Because I will tell you, sometimes I've been at home for 5 minutes before my phone thinks I'm at home. And sometimes I'm not even there yet. I'm at the edge of the neighborhood, and it shows that I'm there. Because it's giving a limit approach to me being there. That's what it's doing. I'm getting close, right? It's limiting. There's 3 different types of limits we're going to do, and if you'll notice, the only difference between all 3 of them is what happens after the number, in this case, 3. The first one has a plus, the second one has a minus, and the third one doesn't have anything. So when we're looking at limits, we're looking at limits from a graphical approach, okay? A 2-dimensional graphical approach, by the way. So we can only get close to the x value of 3 from the positive side of 3, or the right-hand side, or from the negative side of 3, the left-hand side. So when we have a little plus after this, this means from the positive side, which is the right-hand side of the graph. The way that we read this is the limit as x approaches 3 from the right of f of x. So we kind of read top down, like the limit x approaches 3, that part first, and then we pull the f of x in as the second piece we read. The next one, 3 negative, means from the left, because that's the negative side of the graph. So the limit as x approaches 3 from the left of f of x. And then the next one talks about has nothing after it, right? There's nothing there. So when that happens, it means we have to come from both sides. So if there's nothing after the 3, it means it has to approach it from the left and from the right, both of them. So this one's the limit as x approaches 3 of f of x. Okay, so let's look at this then from a graph. Okay, so this is one of those things why the notes is really helpful so that we don't have to spend as much time to write them down. Everything you're seeing on my screen, if you don't have your notes printed, the only part you would have to write down is the part that's underlined. If you don't have notes printed, you're writing down everything, which is more, obviously. So we would say that a limit exists if and only if both corresponding one-sided limits exist and are equal. So if we come from the right and we approach the same value as we come from the left and approach, then the limit exists. Another way of writing that in notation is to say that the limit as x approaches, and I'll just use an arbitrary letter a as my number, it could be the 3 we used before. The limit as x approaches a of f of x is equal to L, our limit. IFF means if and only if. If and only if the limit as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x, and both of those are the value L. That's the notation that we're going to become more familiar with. So I'm going to try and use it a few times to just help us to be able to identify it more quickly. So if the left hand and the right hand limits are the same, and they're L, then the overall limit is L, and the limit then would exist. Okay, and so now we have a picture, and you're going to have to draw the graph in order for us to make sense of it. So let me give you a second, because I know a few of you are writing all this down at the moment, and you need the graph drawn, or otherwise you're not going to be able to do the problem. So go ahead and draw this graph. Our question is going to ask us to decide what each of these limits are, or if they don't exist. Make sure and note we've got a closed circle in one spot, we've got an open circle in another spot, and we've got some grid markings. We've got some grids pieces marked there, whatever, as well. That'll be helpful for us. Okay, the first three listed here, A, B, and C, all use an x value of -1. So everybody see that? Okay. So we're all, on all of those, we're going to be looking at this x value down here to identify things that are happening. It's all about x equal -1 on A, B, and C. Now, A says that the limit as x approaches -1 is coming from the right, right? Positive means the right-hand side, right? This is the positive side of the graph. This is the negative side of the graph. So we are coming from, not moving toward, but coming from the positive side of the graph. So in a very real sense, we are moving along the graph like this. And as we do so, and we get close to the x value of 1, it's the open circle that we're getting close to, right? The open circle. What y value does that open circle get close to? The y value is 2, right? It's this 2 right here that we're getting close to on that. So we would say that this first limit as x approaches from the right on that -1 value is 2. All right, the next one, I'll change colors. We'll use red. We're approaching from the left side, the negative, right? It says negative after it. So we're going to approach like this. Now, it's not a very exciting approach because it's actually the same y value all the way along that particular piece. That's okay. What y value is it?
1.
It's 1, right? So over here, this one's 1. Now, if you remember what this is saying over here and over here, what we're looking for, that third line down here, is we're looking for what happens from both directions when there's nothing after the 3. Over here, we're looking at what happens from both directions when there's nothing after the -1. So from one direction, we get close to 2, and the other direction, we get close to 1, and in particular, they don't match, right? They just don't. If they don't match, then the limit does not exist. D&E is how I would write that down myself. Feel free to write it out if you wish. It doesn't exist. Now, pretend for a moment that it didn't say 2 and 1. It said 2 and 2. If it said 2 and 2, then part C would also say 2, right? It would just match them. So if it matches, it stays the same. If it doesn't match, it does not exist. Now, I'm going to clean the red and the green off of my graph, and we're going to take a look at the number, or the letter D. We no longer care about x equal -1, because it doesn't say that x is approaching -1. It says x is approaching -2, right? So -2 is over here. Now, we do the same thing. It's just that it isn't identified in 3 parts. So even though it just says x approaches negative 2 and it doesn't have an x approaches negative 2 plus and an x approaches negative 2 minus, we still have to do the x approaches negative 2 plus and the x approaches negative 2 minus. So in terms of the red one, because that's what I've got up here, I'm still going like this. And I'm kind of pausing as I get to the negative 2. And in terms of going from the right-hand side, it's okay if you start over here on this piece, but eventually you're going to jump down and you're going to move over here. The graph keeps going. Right? Just imagine a child jumping across the mud, the mud puddle, right? Not walking through it, jumping. Okay, so they jumped across. And what value, in this case, are they approaching?
1.
It's still 1. And it's 1 from both directions, right? They are approaching the exact same place. So the limit for D is actually 1. Okay, our last one, part E, x approaches 0. Where's 0? Yeah, it's the center point. So it's the 0 is like right here. I don't really mean like that's the spot on there, but this is x equals 0. It's the y-axis, right? I'm approaching whatever value I'm at on the y-axis. So again, if I'm going from the right-hand side, I would be doing like this, and I'd be pausing there. This time, if I'm coming from the left is when I make my jump. So I'm coming from this direction, and I'm jumping up to here. So it's not at a like grid marking, so we're going to approximate. What would you say that looks approximately? It is the same value from both sides. I should have said that, right? It is the same value from both sides. What value does it look like it is approximately? 2 point something. 2 point what? 2.8, maybe 2.7, maybe you wrote 2.6. Something in there, right? It's a little more than 2.5. Yeah, but it's definitely not at 3. Okay, does that make sense? All good? All right. Let's take a look at the next one. We have time for at least one more, I think. This is the numerical one, okay? Notice from the get-go, my tables don't have 3 columns, do they? That is better, right? In 1.1, my tables have 3 columns. This table only has 2 columns. It says create a table of values for the function and use the results to estimate the limit. Okay, so we're approaching x equal 3. Now, when we did that example earlier in section 1.1, we were approaching x equal to 2. Remember what we did? We did 1.9, 1.99, 1.999, 2.1, 2.01, 2.001, right? We're going to do the same thing on this one, but at 3. So instead of doing 1.9, we're going to do 2.9. And 2.99 and 2.999. And then instead of the values getting close to 2, we're getting close to 3. From the upper sides of 3.1, 3.01, and 3.001. So this is the same process as before. And your table's already set up to accommodate. So we put this value into y1, and we report the outputs on the f of x as we list them down below. So into y1, and again, you may have to do parentheses around the numerator, parentheses around the denominator, depending on how your calculator sort of responds to that, or the version that you have. So we're going to put x squared minus 9 on top, and we're going to put x minus 3 on bottom. It's probably worth noting on this one that you can't actually plug in x equal 3. Why not?
Because it equals 0 on the bottom.
Yeah, the denominator would equal 0. We can't divide by 0. That's an undefined operation. So while in the example we had in section 1.1, we could actually plug 2 in, we can't actually plug 3 in here. We would have to plug in a value getting close to 3 as our best guess, which is what we're doing. So if you put into your table 2.9, remember that second graph, 2.9, 2.99, and 2.999, and then 3.1, 3.01, and 3.001. You get values that show up and they look really nice. In fact, they don't even like shortcut them on the y value. So if you like arrow over in your table and like we did last time just to make sure that it doesn't expand any further, they actually don't. What is 2.9's value?
5.9.
5.9. What's the next one?
5.99.
And
5.999.
and if we went down this table, what does it look like the f of x value is getting close to? Looks like 6, yeah. So let's check and make sure, because we have to check both sides of it to make sure it really works from both sides. What if you put in 3.1?
6.1.
3.01?
6.01.
And the last one?
6.001.
And as you go down this table, you get also 6, right? So our limit value here, the limit equals 6. Or it's at least approximately 6. It does equal 6. We didn't really prove that it equals 6. We proved that it gets really close. The limit is 6. And look at 2 compared to 3. What changed? What changed?
So plus sign.
Positive sign in the numerator, right? The sign between the x squared and the 9 is now positive. That means you can make a very slight change in your calculator at the moment. Change the sign to be positive on top. And all of our x values will be the same as the previous problem. I have 3.1, sorry, we did 2.9s first. 2.9, 2.99, and 2.999. And 3.1, 3.01, and 3.001. We don't even have to enter them again. They're still in the table. And it even already gives you the y values that you need, but they have changed significantly from the last problem. And all we did was change a sign. Signs matter. So if we look at our f of x and we enter those now, let me change mine just a second. We see that the first one is now negative 174.1. And then we have negative 1794.01. And I have negative 17,994.001. What does it seem like is happening as I go down this table? First of all, it's negative, right? Negative what? What do you think? Well, it's getting infinitely large and negative. So we say it's approaching negative infinity, right? Every single time I add one more 9 to the end of my 2.9 list, it gets 10 times as big as it was before, right? It went from 174 to 1,794 to 17,994. Let's do the other list. On the other list, it goes from 186.1 to 1806.01. And it ends, my last one at 18,006.001. What does this table seem to have happening? Infinite, right? So one was negative infinity. I don't know why it's down there so low. But one's negative infinity, one's positive infinity. Do they match? No, one's positive, one's negative. They don't match. And even if they did, infinity is not a number. It's a concept. You can't approach infinity like not as a number. It's not a numerical location. You can't ever get there. Yeah? You can't even get close to there. So this limit does not exist. All right, this is a fantastic spot for us to stop in because what we're doing next is actually far different, and we'll pick up with that next time. This is open on WebAssign, by the way. So if you wanted to start 1.2, you may, and that's fine. It won't be due until Friday, but 1.1 is due on Wednesday.